Our speaker today is my friend and colleague, Dr. James Cleverley. Okay, my internet connection is really dodgy today. Can everybody hear me?
Yes, at the moment.
Okay, I'll go very quickly then. James completed his PhD in hydrothermal geochemistry at the University of Leeds before moving to Australia. He joined James Cook University as a postdoc in the Cooperative Research Centre for Predictive Mineral Discovery. Following this, he joined CSIRO in Computational, Geoscience and X-ray Characterisation and was later involved in the Deep Exploration Technologies CRC. James joined Imdex in 2014, where he has learned much about the process of commercialization of technology and the challenges of introducing new disruptive technology products to market. Experience in academia, applied research and business, and being exposed to the challenges of the mineral industry in a range of commodities has been an amazing experience, but may have led to a few grey hairs, which I don't have to point out. In this talk, James will discuss the way data is being generated quicker and workflows for turning that data into information using robust QAQC and exploratory data analysis with analytics. There will be a chance for question and answers later, but go for it, James.
Excellent. Well, thank you, Nolene, for inviting, and thanks to everyone for turning up. Apologies for the lockdown hairstyle. It turns out that hair clippers are as rare as gold bars in the UK at the moment. So we're all in the same boat. At least I've made it to the office today. So I guess what I wanted to touch on today is really where technology and software systems have developed to enable us as geologists to get access to data during the process of drilling or field sampling, to get access to quick data to inform or help us to support us to make the right decisions or decisions at a good time. And I'm going to sort of touch on the kind of some of the technology aspects, but then kind of take you through a couple of examples, worked examples, of some of the data exploratory analysis that can be done. Touched on a few methods. It won't be a really in-depth touch on those things, but just give you a sense for the kind of things that can be done. The problem, I guess, that we're trying to solve in the industry, one of the things that we're trying to really drive our technology to solving is the problem of time. And if you think about an exploration program, a mineral exploration program focused around a drilling program, for instance, that program is a cycle. It's a cycle where we drill a hole to take a sample, to measure properties within that sample, to make an interpretation of that data. And we do that to make a decision about what to do next. And typically we'll go around again. Now, obviously, if it's in a diamond drilling environment, greenfield diamond drilling, that cycle could be anything up to 6 months, a year to move around. It takes that long to get the data sorted out. In a blast hole environment, that cycle might be, say, 72 hours to get your assay back, your grade assay, to make a decision about how to blast. But in all cases, really we want to do it quicker. And the efficiencies in the industry going forward are around the fact that we need to move around this cycle quicker, because actually this is a risk decision cycle as well as a drilling cycle. So as we go around this cycle and make decisions, we are de-risking our projects as we go. It doesn't matter what part of the mineral cycle we're in. And really, what we're really after as geoscientists is rock knowledge. And what is rock knowledge? Well, it's really about 4 components in the rock. It's about the texture, it's about the mineralogy, it's about the location that sample was extracted from, be that on the surface or be it underground in a drill hole, and something about the grade or the chemistry of that sample. And really, with those 4 properties, if you understand those 4 properties in your rock sample, in your block of rock, you can use that then to inform many of your decisions down the track, be it trying to discover an ore body in the first place, all the way through to how do I process this and extract the commodity element of choice. And there's many methods for, I guess, collecting those bits of information. I mean, for texture, it could be imagery, it could be the petrophysical signal that we see in the rock. For geochemistry, of course, we have technology like Portable XRF, like LIBS, handheld LIBS now just emerging onto the market to give us that geochemistry quickly. This is about in-field quick assaying. The mineralogy, there are technologies like Portable XRF, visual near infrared, kind of spectrometers, the halo, those kind of things. And then the location in a drilling program is about really knowing where that sample came from. So that's about your downhole survey. That's about the kind of things like their core orientation, so knowing what orientation that sample was in. So there's a lot of technologies there that are required to inform us about the rock knowledge. But then, of course, it's not just about data. As geoscientists, we want not just the data, but we actually want information products. When we make a decision, it is not on the basis of raw data. It is on the basis of an information product. It's the information we extract from that data. Here's just an example of some downhole plots. Here's an example of a downhole plot. Here's some logging, some geology logging on the left-hand side. There's a gamma trace in red, a natural gamma log there, and some Portable XRF data, potassium, iron, some gold assay data here. And what we've done is we've taken all of this data and done some analytics on it. We've actually done a classification. It's a self-organizing map in this case. That's a sort of unsupervised learning method. And so then we're turning that into an automated classification based on all of that data. So yes, you can see the data, but now I can see a classification that allows me to make a decision. You know, am I in an arsenopyrite dominant or an arsenopyrite disseminated zone? How would I process that ore? And really it's about trying to deliver these information products as quickly as we can. One of the ways that we're trying to achieve to do that is to get the data where we need it. We don't want to be passing CSVs around, emailing data, writing bits of data on post-it notes, because that's going to slow this whole process down and leads to errors as well. We don't want to be sat in our session with something like iGeologist, ready to analyze our data and spending enormous amounts of time cleaning that data in the first place. We want that data to come through cleaned, validated, QA'd, ready to do the really fun stuff, which is understand what it's telling us. And so there's various systems out there, there's various ecosystems developing in our industry for allowing data exchange without sort of having it going through files and those kind of things. In Imdex, we've got our Imdex Hub system, which is a sort of cloud-based system for exchanging data from our tools to the customer. But we're also working with a lot of third parties to push data around. Leapfrog, for instance, have their Sequence Central product, which allows exchange of data without passing files through. So I think there's a lot going on in our industry around the way that data is exchanged, and in this way is the way it's going to be done in the future. So what are some of the challenges we face around the quality of the data or the data that we receive, and how do we make sure it's clean and validated? I think if we look at Portable XRF, this is something that I've been using. I've been familiar with Portable XRF since about 2002, would have been about the first one I ever played around with. It's a tool that's becoming much more prevalent in our industry. It's a tool that can give you a rapid geochemical analysis and allow you to make a decision. I think without any shadow of a doubt, the hardware side of Portable XRF has evolved and moved to a point where it's incredibly robust and well-used piece of instrumentation. It can generate incredibly good numbers. But where our problems now exist are in the way that we move the data around, look at the data, capture the metadata, the way that the Portable XRFs are used in a workflow, so the user, how that user is using the system. And then now that the hardware is so good, actually a lot of our problems now are in the quality of the sample that we place in front of the XRF. So there's now work to be done across those three aspects to really improve what we're getting out of something like Portable XRF technology. To give you just a heads up, I guess, an idea of what sample quality means. So we're very used to kind of the point and shoot aspect of Portable XRF. You can get that instant answer. And so here's just an example of what it means if you take something like a dolerite. This is actually a Perth Hills dolerite on the left-hand side of the screen there. And we take that and we point and shoot the XRF at that multiple times. I think about 10 or 15 times I've done in this exercise, versus actually crushing and milling that sample and then pressing it into a pressed puck. That's the sample on the right. And the pressed puck, of course, is the most perfect sample to present to an XRF. It's flat, it's dense, it's homogeneous. And so we're going to compare the data from those two different samples. And if we look at that data, these are two plots. So they're showing us the data extracted from, I think it's about 15 analyses of 2 or 3 different pucks in blue there, and the point and shoot analysis of the rock about 15 times. And what we're looking at there is a set of elements from zinc to silica, calcium, and this bar is basically giving us the range of data that we get out of those analyses, and then the dot is the mean point. And I think what you can immediately see as you look at that graph is that by going through that sample prep exercise, we are reducing the variance we see in our result. And I guess the question is whether that's something that we're worried about or not. So if you look at something like copper, for instance, by pointing and shooting at the sample, you're going to get a result between, say, 75 and, say, 250 ppm copper. It could be one of those. If you do the sample preparation process, then of course you get a number. You get a very specific number. It's about 100 and, just looking now, about 130 ppm. And you're always going to get that same number. Now, it could be that the decision you need to make or you want to make can be made knowing with this amount of variance, and that's absolutely fine. But sometimes we really need to pin down what our numbers are. And in particular, this becomes important for the light elements. And here we can see calcium. And these are now getting into percent variance versus a very precise answer from a sample prepared well. And so the light elements is really where this matters. And one of the reasons behind that with Portable XRF is that the air, those X-rays coming from the light elements are very low power. They're very lethargic and lazy X-rays. The air absorbs them, and so that any air gap, any gaps in our sample, so the sample's not packed correctly, all of those things will contribute to a reduction in the intensity and giving us the wrong result. But worse than that, you actually get different attenuations of those X-rays depending on what element it is. So here we've got a plot of magnesium versus magnesium calcium ratio. Everything from flat analysed on a puck to 1 millimetre air gap to a 2 millimetre air gap. These are not big numbers. And you can see how the concentration of, reported concentration of magnesium goes from 3.1% down to 1.8%. And the ratio, more importantly, changes from sort of up here at about 0.45 down to 0.3. Now, why is that so important? Well, if I want to make a decision about what the classification is of my rock that I'm analysing, if I get a result here versus a result here, I'm going to classify that rock completely differently. So if that's important to me, then I need to kind of put that extra effort in. And so for things like geometallurgical analysis, where the light elements become so important, lithogeochemistry, then those analyses are really, really prone to these issues around sample preparation. So you have to do that kind of job well. So you can see here a classification diagram and how the data points could move across that diagram based on your sample preparation. So the Portable XRF will give us good data if we do a good job, and we need to understand what decision we want him to make to know what we need to do with the sample before the Portable XRF analysis. One of the things we've been doing in Imdex to solve that issue is to build technology then to deal with the sampling, to deal with the data flow through these systems. So here we've got our lab rig for coarse material, which is a portable crusher, portable mill, your press for the puck, and then presenting that to the XRF, capturing that data correctly with the right quality control, and pushing that data through to iGeologist, for instance, to do the data analysis. I'll show you some of that in a minute, to give it to the geologist. So this is how we're trying to solve some of these challenges. So what's a good example of a data to information flow that we've done before? So sort of going through different data sets that I had, and this is a good one. So this was actually a project we did with the South Australian survey, geological survey, when they did some regional drilling in South Australia around the kind of Gawler Craton margin. And at the time, we were partnering with CSIRO, Deep Exploration Technologies CRC, and we deployed a prototype of a lab at rig system for diamond drilling. And what we've got then is a set of data collected. I'm going to concentrate on 4 drill holes from one particular area. And what we're doing is we're collecting data every meter, roughly, as they're drilling. So we're collecting geochemical data every meter as they're drilling. The system itself is very manual. It was a proof of concept. It's really just some sample prep equipment coupled in with a Portable XRF and a Portable XRD, in this case, Olympus systems. And what we were doing there was sampling the curve cuttings, that is the cuttings from the diamond bit. We're sampling those out of the back of an AMC solid recovery unit. So these are taking the solids out of the drill fluid, putting the clean fluid down the hole, and we can use that solid material then as a geological sample. Turns out it's incredibly representative, and we can depth it incredibly well. A lot of research around that. Also, what it allows us to do is get the data within 1 to 2 hours of that interval being drilled. So this is really as close to kind of almost real-time analysis at the rig that we have in the minerals industry. So this is a good example. So we're getting this data within 1 to 2 hours of the interval being drilled. We can pass that data through our ecosystem, our data ecosystem, and bring it into iGeologist. So iGeologist is software we're using here to look at that data. Now, as a geoscientist, the first thing that's really good about that is that we know we've got the QAQC done. We know that the data is clean. We're not going to have any database errors when that data arrives here, because we've dealt with that in the way we put the technology together around that, collecting that data. So immediately we can jump in, we can pull that data in, we can plot a few things up, and we can start to look at our data. So we've now got a lot of data in front of us, and what do we start to do? Well, the first thing we do is we plot up something like this. So here's a plot of silica versus a range of elements. These are kind of mostly elements that would be critical in lithogeochemical classification. So as a geoscientist, you sit there and you look at that, and so immediately what you can see is that within those 4 drill holes, there is structure in that data. We're seeing groupings, we're seeing trends. So the typical approach, typical manual approach to this process would be to look at one of those plots. So here's silica versus niobium plotted, just raw data. And what we're doing here is we're just turning on the density contours. So we're going to contour this data. So we've got 2 very dense clusters of data there, and some other bits and pieces of data. Depending on whether you are a clumper or a splitter in the audience, would be whether you felt you needed to kind of draw 2 boundaries around this, or maybe 4 or 5 or 6 boundaries. But as a geoscientist, you can look at that and you can say, okay, I can see that my data is starting to partition. What does that mean? Start to draw boundaries around that data in a very manual sense. Let your brain do the work. And what we do, and so here you can see that I've nominally splitted it a bit. So you can see the graph there, and I've colored it up based on where I can see groupings in the data. I don't know what those groupings represent right now, but I can very quickly do that and very quickly then plot the drill holes. So here's the 4 drill holes we're looking at. We've got, what have we got here? Silica and niobium plotted down the drill holes. And we can see here these colored bars relate to the classifications we've drawn on that diagram. So there's a really nice approach there for classifying on a diagram and then looking at it in a downhole sense to know spatially how that numerical analysis is fitting in with what you're seeing. And just in that very first pass sense, you start to see that there's some consistent boundaries, consistent units across here. And there's some drill holes that enter some units down the bottom here of MSDP1. There's a sort of an orangey color group here, this group here, that does not exist in the other drill holes. But there's some sort of greeny, purpley groups in here that do seem to exist across the drill hole. So immediately, within a couple of minutes, you've got a sense for where some of those key boundaries are and how those boundaries relate to geological units that you're seeing in your data plot. And then as a geologist, you could be having that in your hand and go and look at the core and say, okay, what does that mean now in the core? What do I see in the rocks that relates to what I'm seeing in my hand and in my analysis there? So that's the kind of what I call the instant gratification approach. That's just getting in there, pulling your data apart. There's lots of ways in something like iGas, in some of these systems for pulling data apart. You're looking at the way data is correlated, the way that it falls apart. But as you saw back in here, to start to kind of try and do that across anything other than a bivariate plot, maybe a ternary plot, becomes really complicated. The human brain really struggles with that process. So at that point, we want to move to other kind of more machine learning techniques. And so one of my favorites, people that know me know that I like self-organizing maps, is the self-organizing map. This is unsupervised learning method. What do I mean by that? This is an artificial intelligence method, a neural network method that actually lets the data inform how it wants to self-organize, how it wants to cluster. So we're not imposing categories on it and then getting us to classify future data with already pre-existing categories. We're just saying, let the data pull itself apart in the way it wants to. How does it want to self-organize? For those that don't know what a self-organizing map is, the way that I describe it is if you think about a football stadium full of 50,000 people, and every one of those individuals has a certain height, and a certain eye color, maybe a certain age, hair color, a bunch of properties. What we're going to do is we're going to build a random classifier, if you like, based on all those properties. And then we're going to basically ask or go around and start to organize those people into different groups. So what they're going to do is that person, you're going to point to a person and he's going to go and stand next to someone that has the most similar features to him. And you're going to go through every person and do that 50,000 times, and then you're going to iterate again 50,000 times. And slowly, that population will self-organize into clusters that will have the most self-similar features. And that's what a self-organizing map is doing. So I've put a bunch of lithogeochemical elements in here. I've done a transform of that data called a centered log ratio. That is actually just to remove the problems we have in major elements around closure problems for our geochemistry. And I'm going to run a self-organizing map. So these are the kind of outputs. It takes probably a couple of minutes to run on a data set like this. And it's going to go through and it's putting that data into clusters. Okay, so this U matrix here has a setting. You can think about this like a topographic map. There are clusters separated by ridges. And the higher the ridge, the more different that cluster is from that one there. We then go through and we cluster, we find the boundaries of those clusters and we're coloring them in this case here. And so these are places where the data is most self-similar. And we're letting the data tell us where it wants to be. We can then apply that back to our data set and then we color it up based on that original data file. And one of the nice things about SOM is you can save a self-organizing map. So if you've got new data in the future, you can actually apply that SOM straight back to the new data and classify the new data. So in a drilling program, if you generate something you're happy with in drill holes 1, 2, or 3, you can then be applying that to drill hole 4, 5, and so on as a classifier for your data. Very quick to do. So here you go. So here's the coloring, here's the classifications that the data is telling us about. There's maybe a few places you could argue you would put a sub-boundary in. So up in the silica titanium, you can see there's a more titanium-rich group. But more or less, that's done a pretty good job. And it would be very hard to do that as a geoscientist, just manually coloring those things. But one of the nice things, of course, then, is you can take those groups back into the downhole plot. So we're going to bring that back to the geology. So I'm going to plot it back in my downhole plot. And I'm going to see what I'm looking at. And you can immediately see that we've got some. So here's the purpley orangey groups. And that seems to be the same here and here. We've got some blue groups, these green to orange, green to orangey colors at the top here. So there's certainly things in these drill holes that seem to start matching up units. MSD PO2 drilled away from the other holes looks like it's going through very different geology. And so immediately you go, okay, well, I can see that straight away. And you can take this data, and the really important point here is take this data, go back to the core and support you to be a geologist making decisions. So you can see where those boundaries are, and you can start to make decisions about what the rocks are telling you relative to how you've classified this. So that's just a really quick example of how we can go through and do a kind of a rapid classification of data that might be coming from the drill rig very quickly. Once we've got those classifications, it is about then knowing what they mean. And you know, there's lots of techniques then for going back and looking at the data and saying, what do these data sets mean? Here's a principal component plot, for instance, that shows us that we've got a very dominant trend in the data, particularly from 3 of the drill holes, where we've got some more mafic components, titanium, iron, magnesium, nickel, going in one direction as a vector, and your more felsic components, your potassium, your thorium, those kind of things going in the other. So we've got this bivariate distribution that seems to be related, but obviously something very different is happening in the rocks we've drilled in MSDPO2. So these are all decisions that could be made at almost the same rate that I'm talking in this talk. But your drill rig in this case is still drilling. It's not that you're looking at this data 6 months later after the drill rig's already gone. You can make decisions about what to do next, keep drilling, move somewhere else. Just to talk about one other thing, so the wavelet tessellation is another feature, and this is about how do we bring things back to the core and support the geologist that's logging. Wavelet tessellation is a way of taking a downhole trace, or it could be a time series as well, and it's picking the boundaries for you. So this was developed by June Hill at CSIRO, and we commercialized this a few years back and have put it into the iGeologist software platform. What I'm actually doing here is something a bit fancy, but I'm actually doing a wavelet tessellation down these 4 drill holes of the first principal component. So this is the thing that describes the most variation we see in the geochemistry, and we can see immediately where those key boundaries are. And one of the really nice things about wavelet is that it gives you the coarsest boundary on the right, coarsest domains if you like, and the finest scale features on the left. So as a geologist, you can go out to the core with this in your hand, and you can see immediately where those key scale boundaries or major boundaries are, where the biggest domains are, and where the finest scale features are. And again, in your logging process, you've got this to support you to do a much better job of logging. Don't forget, some of these features could be in very black looking rocks, so you might not otherwise have picked these out as it is. So that's just another tool to allow you to support the person doing the logging process. Now I am running out of time. This is again the wavelet tessellation, but in this case for copper in this case here. So just the raw copper, showing you how you can do it for different data sets. Now I am running out of time here, so I have got another example here for remote sense data, but I might just move through this quite quickly, and I'm happy to distribute this PowerPoint or something for people to have a look at. This is actually taking radiometrics, raw radiometrics data, doing the same self-organizing map analysis process to actually build, in essence, a classified map of the area based on the radiometrics. And this map here, this is over the Kintyre uranium deposit. This map here matches very, very well to the regolith map that GSWA have produced. So here you might take remote sense data and give yourself a classification map that you can then go into the field and test what it means. So what does it mean to be this iGeologist, a future geologist, who's now got available to him technology and the data infrastructure to do these kind of analyses very quickly? So technology is now available. It is available right now to collect quality data, and it's about quality data. You need it to be quality to do the best analysis, and you can start to do that at the time of drilling and use the software to extract information. And it's about collecting that and delivering that information to support the geologist to make a decision. And so put it in the hands of that geologist as they're looking at the core for the first time. Give them much better tools and information to support them. Really interesting question though, based on what this looks like, is what training and education looks like for our graduates, for our early career researchers, for people in the industry. And I think it's going to require good geoscience, but with this sort of background in numerical understanding and technological understanding that's going to be so critical going forward. And I think one of the other points I was just mulling over this morning when I thought about doing this talk to all of you online is that I think the COVID-19 experience is leaving us with a much better feel for how we can start to deliver not only the kind of data and understanding and analysis in this way, but our training online as well. So people, a lot more people should have access to the breadth of training that's required going forward. And I've just come off a 4-day iogas training course. It was all conducted online with 70 geologists. So I think we've learned how to do this now, and I think that's a good timing for us in the industry. That's positive from where we're at. So I think I'll leave it there and open up for questions. Nolan.
Thank you very much, James. That was very interesting. We are open for questions. You can raise your hand or unmute your mic and have a go at it. I'll start the process by just asking one question. I mean, getting data and interpretations basically at the drill site is going to shortcut things remarkably, I think. But you didn't say too much about quality control in the field. And it seems to me that's going to be an important aspect of getting this right. Yep.
Yeah, absolutely. And you know, I could have put a whole section in there about sort of rapid or real-time QAQC. You know, one of the things that, you know, so yeah, one of the things we've written is a piece of software that connects Olympus Portable XRF to our Imdex hub system. And one of the key reasons we wrote that application, wrote that software, was to build in stringent QAQC processes as part of collecting Portable XRF data. So that when you get that data and it's delivered to you as a geoscientist, and you're sitting in an office maybe in Johannesburg and there's a project in the middle of Namibia or something, is you can see that QA data coming in every day. You can be confident that everything's working okay, that everything's performing as it should do, and that all of that QA is being followed, and you know, enforce the rigor, enforce the auditability of those processes against that person. That's going to be a really important jigsaw piece in this future state. Absolutely, Craig. Couldn't agree with you more.
Are there any other questions or comments? Now is your chance to jump in.
Hi, James. It's John Arthur. Just a quick question on the type of deposits that this is more applicable to. I'm thinking, you know, if you've got a large copper deposit and you've got a fairly uniform mineralization over large zones within the core, compared to something like a shear zone gold deposit where you've got very high variability of grade over short distances, even within individual samples. Is there a point at which this system starts to have problems, or would you say it's applicable to all scales of mineralization?
Well, yeah, I suppose that that comes back to, you know, so some of the fundamental understanding about how you representatively sample, what you're sampling for, the kind of geochemical elements, for instance. I mean, I'm using an example of Portable XRF, but the kind of geochemical elements that you might look at. So, I mean, one of the things I always talk about is when I'm faced with a big data set is, am I thinking in the first instance about lithogeochemistry and the geological packages? Am I thinking about hydrothermal alteration? Am I thinking about some of these other factors? Because the subset of elements you use might be different. So if you look at what I just showed then, I didn't put any of the kind of ore components into that analysis because I was trying to look at rock type. But then you start to put some of those other elements into the package, and we start to see features of the alteration, and that could operate over a different scale than the rock types, and that's really important. You know, of course, there'll always be geochemical elements that are, you know, in terms of in-field geoanalysis, which is rapid and it uses, you know, techniques like Portable XRF, LIBS, or something like that. There'll always be components that are more challenging to detect at the right levels: gold, platinum, palladium, those kind of components. So I think there's always a sense that you're doing this to make a decision, but it might not be the end point. You're still going to then, you know, you're going to use this data to actually, and if you look at the wavelet tessellation there, I'll go back to that, you can use this data, for instance, to inform how you might sample that core and send it away for that next level of analysis. So I think that's the kind of way I think about this a bit in terms of whether it's applicable or not. I think Still, this is applicable even if you can't analyze the gold directly in real time. Some people are trying to do that. You've still got all of those other components to allow you to have a much better systems understanding and still be able to make a decision, still be able to prioritize which sample I want to send away for gold assay.
Any other questions or comments? Somebody had something, I'm not sure.
I think it was John Arthur who wanted to say something.
No, I was just saying thanks for the answer. That's very comprehensive. Thank you.
All good.
I don't see any more questions or queries or comments.
Well, as always, I'm totally happy for people to contact me at any point, and you know, if you've got a question, just fire it away. You may tell I'm quite passionate about this, so yeah, quite happy to get into conversations about all of this type of stuff.
We will be lodging this presentation on the GSSA YouTube channel,
Yep.
which so it'll be accessible. Nolene, would you like to conclude the proceedings for the day?
Thanks very much. James, thanks very much for that talk. Again, I enjoyed it. Everybody else, thanks for joining us. Have a good weekend and stay safe. We'll see you next week.
Thanks all. I'll end the meeting now.
Thanks very much.
Cheers, James.
No worries at all.
Thanks, James.
Cheers, James.